So, any specific questions you guys have? I'm thinking to discuss. So, since your week, so when is the deadline for week 5? Is it over or is it still there?
Yeah, it's over.
Week 6?
It's on 22.
Okay, so I'm planning to discuss on week 6. So, if you have any particular questions regarding week 6, you can, let me know. Otherwise, the topics in week 6, just to let you know, guys. Convolution, properties of convolution, and convolution with direct delta function, and LTI systems. Uh, they have separate properties apart from the original systems. These properties, identifying whether the LTI system satisfies this property or not, will be little different from what we have learned in the earlier weeks. For example, like we have seen, for the systems that we have seen, there are different kinds of systems. There are linear systems, there are time invariant systems, there are causal systems, there are memory systems. Yeah, there are invertible systems. So all these things we have seen, and there are bipostable systems. So these are all like different kind of systems available. Among the kind of systems those are available, any system that satisfies both linear property and time invariant property, together we are calling it an LTI system, right? And for this particular LTI system, there are again certain properties to be satisfied. And in order, for you to check those properties, the criterion what you see here will be little different from the criterion that you observe here. But there are certain things you also may have to verify for the LTI system. Uh, the such properties are: one is invertibility of an LTI system, stability of an LTI system, okay, mm, causality of an LTI system, yeah, and memory of an LTI system. So the way you check for these properties is little different from how you actually verify these things for the systems. Okay. So if you have any confusion with these topics, we can discuss them. But just to let you know, guys, what topics are there in week 6. I'm just writing them down, and identifying the impulse response of an LTI system, unit response of an LTI system, and so on. Okay, so these are certain topics from week 6. So I would like to cover on these topics. If you have any questions, week 7 we can discuss in the next week. Okay. So any specific questions you guys have regarding these topics?
Yes, ma'am. I have a question.
Yes.
Ma'am, question is e to the power 2t into u in bracket 1 minus t.
So e power 2t.
U
Hmm?
in bracket 1 minus t.
Okay.
Um,
Is
is
this an
professor
assignment question?
no, ma'am. It's a example which was discussed. Professor was
Okay,
discussing in chat.
okay, okay. So this is some
So
signal, right? So is this what it is given, or did he state that this is the impulse response of an LTI system or something like that? I mean, is there more to the question, or
it's an impulse response.
Okay, so this is the impulse response of an LTI system. The standard convention that we follow is we represent the impulse response by h of t. So let me, denote the given signal by h of t. Now, what is the question?
Ma'am, in this question, professor said it's a causal. So how can we? I didn't get how
Okay,
this is
okay,
causal.
okay. So this is okay. That's what I told, what I meant earlier. The way you check for causality when you actually look for the systems is different from the way you look for identifying causality in LTI systems. So let's just go a step back and try to recall like how we actually identify the causal systems if they are not LTA. Let's so there is some system. There is some system which takes in x of t and which produces you output y of t. The standard definition that we learned earlier to check the causality is if y of t depends only on the current and past input values, then we call this particular system as a causal system, right? So this is what something that we learned in our earlier week content. So this is with respect to any standard system. Okay. Now what we have is instead of telling us, the system like the things that were given to us now is that this system is now an LTI system. So suppose you have an LTI system, okay, which has an impulse response h of t. You transmit x of t, right? And your output y of t, as we have studied, is the convolution of x of t and h of t. Okay. So now the question of causality is, whether this particular system is causal and the way that provided like let's not have the short form uh, uh, right now, so let's think about it a moment later, but uh, provided this information, how do you, and also from your earlier week content, how do you check for causality? You try to evaluate this particular convolution and try to evaluate your y of t, the output signal, and you also calculate the convolution and see if the final convoluted output, okay. So you see if this particular final convoluted output is actually depending only on x of t or the past values of x of t. Okay, so if this particular convoluted output depends only on x of t or on the past values of x of t, then we definitely can say this particular system is causal. Okay, so this is how we do, provided we have the knowledge from our previous weeks. Now, what the current week content is doing is it is simplifying this problem much better. Like you don't need to calculate the whole thing, but you can talk about the causality of this particular system just by looking at the impulse response of the given LTI system. Okay, suppose if you know that the system is LTI system, okay, and suppose if you are given the impulse response, so this is the output, and the way we check for the causality is we calculate this output, which is the convolution of the input and the impulse response, and you see if this convoluted output is actually depending only on x of t and the past values of x of t, only then it is causal. But what I'm telling now is you don't need to calculate this convolution just by looking at this impulse response of the LTI system. You know, just by having a look at this impulse response itself, one can talk about the causality of the LTI systems. And how do we do that? So we call this particular LTI system. So LTI system is causal. So this is one of the properties of LTI systems. Okay. So we say LTI system is causal if h of t, the impulse response, is equal to 0 for all values, for all negative values of t. Okay. So if this is true, then we say, even without evaluating this convolution, we can say, that this particular LTI system is causal. Okay. So to answer your question, in this particular impulse response, for the given impulse response h of t, which is e power 2t u of 1 minus t, and what is u of 1 minus t? So u of 1 minus t is uh, 1 for all t less than 1, and this is equal to 0 for all t greater than 1. Correct? So hence this particular system, the given impulse response, is e power 2t for t less than 1 and 0 for t greater than 1, and this does not satisfy the condition, you know for an LTI system to be causal, h of t should be equal to 0 for all negative values in t, but for all negative values in t, h of t is not equal to 0, hence this system is not causal. Does that answer your question, Satru?
Yes, ma'am.
Okay. Any other questions or topics you guys would like me to do? I need some inputs. Any particular topics you guys want me to discuss? Likewise, there is also difference in this Bibo stability. So, in our earlier weeks, the way we look for the stability of the system is we try to evaluate. So, we take a bounded input and we see if the particular system, the output of the system, so if this bounded input implies bounded output or not, right? So this is how we check for the stability of the systems. But when we have an LTI system with an impulse response, so suppose you pass your input signal uh, over an LTI system with impulse response h of t, and you get an output which is nothing but the convolution of the input signal with the impulse response. Now, if you want to check the stability of the system, traditional way is to check if the bounded input gives you the bounded output, that is for the Bibo stability. But when it comes to the stability of the LTI system, the way you check for the stability is you just see if the integration over the entire time domain of the absolute of this impulse response, if this is less than infinity. So if this is less than infinity, then it implies that the LTI system is stable, otherwise not stable. Okay. So likewise, even for the memory, so for the memory, how do you check? So you check if the impulse response h of t is of the form delta a times some del of t. In other words, the impulse response should exist only at 0. If it does not exist at any other places, like no other places apart from 0, then we say, such a system is memoryless. Okay, if the impulse response is in this form, then this is LTI system is memoryless. Or if you can find the inverse of the impulse response, then it is invertible, and we can do other things. Okay, so there's a slight difference between how you check it for the standard systems and how you can verify it for the, this is a simplified case. So in systems we have several kinds of systems, and one of the kind is the linear time invariant system. And when you have a linear time invariant system, like there's a nice simplification on how you can check these properties. Okay, so yeah. So yeah, the topics are very, at least with respect to the topics, there's nothing much to discuss about these topics in detail, except for the convolution formulas. I think we already gave enough information in the last two live sessions, I think. So if you have any specific questions, we can discuss them.
Ma'am, for invertible, what we can do?
Okay, for invertibility, the idea is, let me, if I'm not, not more confusing you guys, let me just go back to what we learned in our earlier week. So what did we learn in our earlier week? So there is a signal, input signal, that we transmit over some system, some random system. Okay, and you get some random output y of t. So you transmit your input signal into some random system, and you get some output y of t, which might depend on x of t. We don't know how it is. Okay, so let me call this system, let me denote it by some f, as in, so y of t is the output that we obtain by applying this system on the input signal. Okay, now, what did we learn earlier? So, what we learned earlier was this particular general system. So, general system, I mean, I don't know whether it is linear or time invariant, I don't know all those details. So, if you're given some general system, and if you want to check for the invertibility of that general system, the way you proceed is, this y of t is some random function of x of t. And what you do for the invertibility, you check if this f inverse exists. So this is question mark. It may not always exist. So if f inverse exists, then we say it is invertible. Otherwise, it is not invertible. Okay. So this is what we learned in our earlier weeks. Now we have an extra information. We know that the system is LTI. So this is an extra information that we have. So since the system is LTI, we know how this f function works. How does it work? So when you transmit some input signal into the LTI system h of t, the output y of t, so f of x of t, when f is LTI, we know this is nothing but y of t, which is the output of x of, this is nothing but x of t convoluted with h of t. Okay, and now the question is, okay, so you have to verify for a particular LTI system if there exists a H inverse function. Okay, so can you the reason why this is true is because of the cascading property of the, so LTI system, like you have to check for a H inverse function such that your final output should be x of t. The reason is we have studied about the cascading of LTI systems. So when we cascade two LTI systems in the cascaded, so when such a transformation happens and when such a H inverse exists, assume if this exists, okay, then what happens is, let me call this x hat of t, okay. So x hat of t would just be x of t convoluted with h of t convoluted h inverse t, and you can show that this would be del of t, and x of t convoluted with del of t is just x of t. Okay, so what you have shown here is, so earlier till this point, what we were checking is if there is some function f associated with the system, we check if there is a reversible function f inverse such that from the output you can get your transmitted input x of t. Now, what we know is that the system is an LTI system, and when it gets transmitted into the LTI box, the output would just be the convolution of the input signal and the impulse response. Okay. Now, what we have to check for is, if for the system to be invertible, there should exist some invertible function for this impulse response. Okay, only if this invertible function for impulse response exists, only in that case you can retrieve back your transmitted signal x of t. Okay, so just to cut it short and make a point, for LTI systems, you check the property of invertibility by looking at the impulse response. If h of t is the impulse response, we may have to verify if h inverse of t exists. If this exists, then it is invertible. Is that okay, Satyam? Hello?
Yes, ma'am.
Okay. Any more questions? We are, I mean, at least I'm deliberately not giving the solutions for the, I mean, solutions are not being uploaded. Are week 5 solutions uploaded? Did I give solutions for week 5? I think from week 6 I'm deliberately not giving the solutions because you guys will be active in live sessions. So if you have any questions regarding the assignments, or if you're not able to solve the assignment problems, you can ask me in the live sessions. Maybe I'll help you out in the live sessions. If I'm providing you the solutions, you guys are relying on the solutions. I mean, after the assignment submission. So it's better to, maybe we I can collectively upload the solutions for all those weeks after the quiz. Okay, so I think for the next assignments I did not give the solutions to the team. If you have any questions with respect to those assignment problems, you can ask me in the live sessions. Mm, I'll upload the solutions to the assignments after the quiz, maybe after week 8. Okay, your quiz is coming up on August 7th, by the way. Okay.
Ma'am, I have another question.
Mm-hmm.
It's uh, summation sign
Mm-hmm.
n equal to minus infinity.
N.
Yes, ma'am.
Okay.
And delta function in bracket t minus n t capital.
Okay.
Yes, ma'am.
Hmm.
And asking
Question
for this
is
memory.
asking
It's a
for.
memory. It's memoryless or memory with or causal, non-causal invertible.
So is this the signal? So how is this defined? I mean, in order for you to check whether this has memory or something, is this h of t? Is this the impulse response?
Yes, ma'am. It's an impulse response.
Okay. So this is the impulse. So that is very important. Okay. So you cannot miss that. So when you say this is the function, you should also know like what this function is. Is this the input to the system, or is this the impulse response of the system? And also you should know, like whether the system is, LTI only, then this impulse response exists. So all those things, all those details are very important. You also need to have it. So given system is an LTI system, mm, so correct me if I'm wrong. Okay. So this is the question, right? So given system is an LTI system, and this is the impulse response of that particular system, right?
Yes, ma'am.
And now you have to check if this has memory or not. Yeah.
Yes, ma'am.
So yeah, as we have discussed earlier, how do we check for the memory of the LTI system? So for an LTI system, okay, if h of t is in the form of a times del of t, or inwards h h of t is equal to 0 for all t not equal to 0, then we say the LTI system has memory. Okay. So to answer your question, in this particular problem, h of t, if you see, this is train of impulses. So this is one delta of t at 0, and we have another impulse, shifted impulse, and another shifted impulse at minus t, minus 2t, 2t, so on. At least this picture is clear, right? So the given signal, this is summation of shifted impulse functions. So when you sum all shifted impulse functions, it is this train. It is also called, so this is a very standard function that they use in communications. Okay, so this is also called as train of impulses. Okay, so this particular signal, as you can see, h of t is not equal to 0 for all t not equal to 0, because h of t at t is defined, h of t is 2, h of t at t is defined, and at 2t is defined, at minus t is defined, and at minus 2t is defined. So h of t not equal to 0 for all t not equal to 0. So for an LTI system to be memoryless, oh sorry, so this is memoryless. Okay, so for an LTI system to be memoryless, we should either have h of t as some amplitude, as some amplified version of the delta function, or h of t is 0 for all other t values other than 0. So in so both, I mean, two cases, these two are equivalent conditions. Okay, so if this thing happens, then we say that an LTI system is memoryless. But in the particular question that was given, we can see that h of t is not equal to 0 at t which is not 0. So at t t equal to t, it is not equal to 0. At t equal to 2t, it is not equal to 0. Hence this particular signal carries memory, or it is not memoryless LTI system. Is that okay?
Yes, and what about other three? Means causality, mutability, and stable.
Causality. So causality, like what did we study? So causality for an LTI system. So if h of t equal to 0 for all negative values in t, then LTI system is causal. So can you tell me now if this particular given impulse response, or the system that is carrying this impulse response, is causal? Given that you have the condition, is this causal? No, right? Why? Because you know h of t for negative values in t, it should be fully 0, but it's not happening in this case. At minus t it is not 0, at minus 2t it's not 0, at minus 3t it's not 0. Always it runs, right? So h of t is not fully 0 for negative values in t, hence the given system is not causal. Okay. And to check for the stability, stability is a workout. So to check for the stability, what you're supposed to do is you have to integrate it from minus infinity to infinity, sum over n from minus infinity to infinity, del of t minus nt dt. You have to verify if this integration is less than infinity. I mean, there's also a mod over here. So you have to check if this integration is less than infinity. The way you can do is, integration is like a summation, so you can just, replace integration and summation. But there is a mod over here. But anyways, so this is like, this is a workout. It's not straightforward to see, but yeah, at least I could tell you the answer. This is definitely equal to infinity. My guess is correct, but we can prove. So there's a mod over here. So this is like, mod A plus mod B plus and so on. I mean, the reason why this is equal to infinity, I can tell you the reason, but you can try to prove it up. So um, so you are integrating over all values in time. You're trying to find the area of this whole, you know train of impulses. And if you have just one impulse function like this, which is del of t, you know that minus infinity to infinity del of t dt is 1. And we have infinitely many such terms. We have so many such terms, right? And it's running across all the time, all the real number line across the continuous timeline. Hence, like, when you sum it up, it should eventually give you infinity, but you guys can try the proof of it. Okay. Is that okay? So this is, yeah, to answer, this is not stable. So this is not stable, this is not causal, and this is also having memory. This is not memoryless. Okay.
And for invertibility,
Oh, invertibility again, it's bit of a headache, man. Like, I don't know why you are checking for these things. Usually, people do not ask such complicated things. This would become little complicated. So you may have to check if H inverse exists for this particular function. You can try it out. If it exists, it's invertible. If it does not exist, then it's not invertible.
and how to find inverse function in H
There
inverse
won't
T?
be any such problems in any textbook. If you find it in a textbook, you give it to me. That's a complicated thing to solve. You can try it out as an exercise if you want. I'm not doing it in live session, at least for this. At least for the given impulse response, invertibility is bit of a headache. Or maybe, I don't know. So inverse of a delta function is a delta function. So I mean, I'm not right away getting any thoughts on this. It might be complicated, not really sure. So h of t is given as minus infinity to infinity del of t minus nt, right? So the way you have to check this is, so you pass, instead of taking train of impulses, take something that is simple first and check it out. Maybe you can take something like, h of t is del of t plus del of t minus 1. Okay. And you can see if you can come up with some h inverse function such that, you know, y of t is x of t convoluted h of t, and you have to come up with a h inverse function such that if y of t convoluted with h inverse of t is equal to x of t. Okay, so then LTI system is invertible. Okay, so you may have to think about some H inverse function, or otherwise you can also try to disprove it by cases, so when x of t, so if for two input values, if it produces the same output value, then also the system may not be invertible. So think of some x1 of t and x2 of t, and check if x1 of t convoluted with h of t gives you the same value as x2 of t convoluted with h of t. Okay, so you can also verify. So if inverse seems to be hard, you can also verify for this. If for any two defined input values, if this is true, then definitely this is not invertible, right? Because you cannot come up with a h inverse function such that you get your input signal back, right? So for this particular example, h of t, check if any two values of input, give you the same output. What can such input values be? Hmm, yeah, I'm not right away getting. Maybe you can first solve. I can tell you the steps, you can work it out. So you can try first for h of t equal to del of t. Okay, first check if this particular system is invertible. Okay. And then also try for del of t minus 1. Okay. And if these two are invertible, definitely, the sum of, since this is an LTI system, the sum should also be invertible. But the first idea is to verify and check if the delta of t, if h of t is equal to del of t, is that system invertible? Is that invertible? Can someone tell me? It is invertible, right? Why? Because so x of t, when you pass through some delta function, what you get is x of t convoluted with del of t. We know x of t convoluted with del of t is simply x of t, right? So you can come up with another h inverse function x of t when you pass through del of t. You can come up with another inverse function which is same as the delta function, okay, such that when you pass through this, so this is your h of t and this is your h inverse of t, so you get back your function x of t, hence this system is invertible. Likewise, I think you can also prove for del of t minus 1. There should definitely exist some. So what is x of t convoluted with del of t? Sorry, del of t minus 1. I think this is x of t minus 1. Huh? You can check this out. So this is simple convolution calculation. So if this is x of t minus 1, then you can also come up with another, uh, uh, impulse response, say del of t plus 1 or something, such that this x of t minus 1 convoluted with del of t plus 1 will give you the original signal x of t. So uh, this is an invertible system, this is an invertible system, and for the sum you can always construct uh, you know uh, inverse of this plus inverse of t minus 1, and you can get back your original signal. So yeah, so maybe this is not very complicated as I thought. So the inverse function of this system would also be this system, if I am correct. So the inverse exists, and hence this is invertible. So the inverse also would be same as this. You can verify that, because if this calculation is correct, whatever I am doing here, which you can verify, uh, you know, uh, x of t convoluted with del of t minus 1. What will that give? So if this is x of t minus 1, okay, so then you can actually convolute it back with del of t plus 1 and get back your signal x of t. Okay, so inverse of del of t minus 1 is del of t plus 1. If my analysis was correct, if even if this is wrong, like what would it do? Maybe x of t convoluted with del of t minus 1, maybe it would be x of t plus 1. Again, you can convolute it with del of t minus 1 and it will give you x of t. So either del of t minus t naught will have an inverse del of t plus t naught, or del of t minus t naught will have an inverse del of t minus t naught. This is something you guys need to verify. Okay, at least with the basic understanding that you guys have, this is very simple to verify. You just have to calculate these convolutions and see what is happening. So in either case, for this train of impulses, the inverse function is the train of impulses. Is that okay?
Yes, miss.
Yeah. You
And
can think about it. You can think about it. You can try to solve it. Okay, so may not be very evident, but you can think about it. It's not very hard to analyze as I thought. Yeah.
And ma'am, is it very difficult for every signal to find in its inverse?
I didn't get you. So what?
Means every time for every signal, it is difficult to find its inverse.
Oh, you are asking me, let's not assume this. For some h of t, uh, so you're telling me that it is difficult to find the inverse, right? So is that what you are telling me? Hello?
Yes, ma'am, exactly.
So the idea is you guys don't need to know the inverse of all universal functions. You just have to understand the concept of invertibility. In real world, when it is the time, we may be using some standard signals for which inverse is known, but the conceptual clarity should be there. You're not expected to solve all hard problems during your course study. You're expected to understand the concept, and the concept is we call an LTI system invertible if two cases: if there exists an inverse for the H inverse function, or if you can identify any two input signals x1 of t and x2 of t such that for the given impulse function the outputs match. Okay, so if you can prove any of these two cases, then such a system is not invertible. Okay, if you're not, so if you're not able to identify you know a particular inverse function for h of t, or this condition is true, so in these cases the system is not invertible. Okay, this is the conceptual understanding. That is what is expected from you. You're not expected to identify the inverse functions for every given function. Okay, so you don't even need to worry. Any proper teacher would not try to uh, you know give some complicated h of t and ask you to check if that function is invertible. Nobody is going to do that. The conceptual understanding is important. Okay.
Okay.
Yeah. So mostly even in your assignments, we would be giving you the standard signals which will be easier to analyze only. So there won't be much hardness in at least the questions we set up when it comes to these concepts. Because as you said, like somebody can come up with h of t which is really really complicated, and somebody can ask you to find if that particular impulse response or the system defined by that impulse response is invertible. There's a possibility that somebody can do that, but no sensible person will be doing it, so you don't need to worry. Yeah. In your exams at least. Yeah. Any other questions? But yeah, this is a good problem. You can think about it. Okay, this is very nice to understand. So this might have an inverse, and inverse would also be the same function. Okay, you can think about it again. Any other questions?
No, that's all
Mm.
from my side.
Okay, thank you, sir. But I hope the understanding is clear with respect to these topics. Okay, so convolution, the only way you can get hands on like good experience with it is to solve as many problems as possible. I think we are already giving sufficient number of problems. So 20 questions. So if you see, it's not like 5 or 6 questions we are giving. So every week we are literally giving 20 questions, 20 assignment questions, and 20 graded assignment, and 20 practice. Sorry, 10 graded assignment and 10 practice assignment questions. So 20 is a lot. So yeah, at least like when I did my undergrad, or like when like in the colleges I studied, they usually give us like 4 to 5 questions. So compared to that, like I think we are giving enough number of questions. If you need more questions, like you can always go back and refer to the reference textbooks. There's internet, and there are lot of practice questions available on internet. You can always pick it up as some challenge, and you can always solve it by yourselves. The concept is clear, right? Okay. So yeah, uh, yeah, that is it is. This is something that after the feedback that we have gotten, like we discussed, and I think we are giving sufficient questions. So by giving more, we might load other students. So we don't want to do that. So you can always go through the reference textbooks, find some nice problems, solve it by yourselves. If you're not able to solve, you can put it on your groups and ask your friends to help you out. Have some nice group discussions on that problem. Okay, if you find something really interesting in the textbook, you can always do that, right? You can, if you're not able to solve, you can post it on your group. You're all connected through groups, and none of you guys are able to solve, you can also let us know. If we can help you, we'll help you out. So that's the way it should go. Okay, so try to solve as many problems as possible when it comes to convolution, because this is going to be really important in your later topics. And with respect to the properties, it's just an understanding. So there's something going on with the systems, and systems are defined in particular way. And in those particular ways, we have a particular system that is defined, which is LTI system. And for an LTI system, there are nice enough properties to understand. Okay, you can go through all these things, and you may need to understand what an impulse response is, what a unit response is, and you can work out as many problems as possible. If you're done with your assignment problems, you can go back and work out a different set of problems. Okay. Yeah. So if you have any questions, yeah, feel free to email me. Did you guys email, and did I not get a chance to reply to them? I reply to all emails, right? Kindly let me know in live sessions if I do not reply on time. Okay. At times I tend to miss the emails, but mostly I'll see them. So you don't need to worry. So,
Ma'am,
mm,
in lecture, professor said example of cos omega t,
okay.
and he said that this signal is not invertible.
Yes. So h of t is equal to cos omega t, right? So yeah, let me again state the conditions for you, how to check for invertibility. Okay, so you have to check if H inverse exists, or there's also another condition. If you can come up with two different inputs for which the final output is the same, then also this is not invertible. And how to check if H inverse exists? So you can see if two time values. So how do you check if inverse exists? For an inverse to exist, this is basic function analysis which you have learned in your +1 +2 days, right? So if the function is 1 to 1 and if the function is on to, then there exists an inverse, right? And if the function itself is not 1 1, then there is no scope of inverse, correct? Correct? This is something that you
Yes,
learned
ma'am.
in your +1 +2. Now for the given function h of t is equal to cos omega t, you can observe that for two different values in time, cos omega t has the same value, because how is the cos function defined? It's defined something like this. And for multiple values of t, you have the same value 1. Right? So the function itself is not a one-to-one function. How does an inverse exist? I mean, there is no inverse, this is not invertible. As simple as that. Is that
Hmm,
okay?
yes, and it's clear. But in lecture, professor convoluted with a rectangular function and said equal to 0, and it's not invertible.
I mean, maybe that there are multiple ways to show that, like as I'm telling, you know, there is also another thing to do, but you have a simple way to say that, so it's okay.
Yes, this method is very simple.
Any other questions? I hope live session recordings are available to you on time. I think last week live session is not uploaded, right? Did they upload it? Professor's live session. I'll ask them to upload that as well as students' live session. Okay. Yeah, please learn these concepts properly, and yeah, quiz will be coming next week. Quiz is going to be on topics till week 8. So week 4 to week 8, and we have to discuss week 7, week 8, and the summary of all these weeks in next 2 weeks in another 4 live sessions. Okay, so it's kind of a thing. So maybe what I'll do is next week I will, if it's better. So week 8 videos are also live. So it's better if you guys can watch both. Like if you guys can complete watching week 7, week 8 videos by next week. Okay. So next week, what I'll do is Wednesday live session I'll discuss on week 7 content, which is on Fourier series, and Saturday's live session we can discuss on week 8 content, some conditions, other the Parseval's theorem, Fourier series conditions only. There are certain, it's an extended uh, topic on Fourier series. So we can do next 2 live sessions on week 7, week 8 content, and maybe we can give uh, the last week, that is from 28th to 3rd, that week, maybe for the quiz topics discussion. Okay, you guys can solve as many problems as possible, and we can discuss on those things during that week. And 7th is your quiz in 2 weeks. So please be prepared properly.
And then syllabus for quiz 2 is week 4 to 8, right?
Yeah, week 4 to week 8. Yeah. Standard. First 4 weeks quiz 1, next 4 weeks quiz 2, and then later 4 weeks. Along with quiz 1, quiz 2 is your answer. Okay.
Okay.
If you guys have no more doubts, maybe should we break? Yeah, I think I can end the session if you have no more questions.
Yes, ma'am.
Yeah, thank you.
Yes, ma'am. Thank you, ma'am.
Thank you, ma'am.
Yeah, thank you, thank you,
Thank you, ma'am.
Thank you, ma'am.
thank you, thank you.